Okay, let's consider quickly problem 7.23 of Sonntag. Power plant generates 150 megawatt of electrical power. It uses a supply of 1000 megawatts from a geothermal source, rejects energy to the atmosphere. So if this is the geothermal spring rock, so geotherm. So we have a supply of 1000 megawatt. It is working in a cycle and it is generating 150 megawatt of power. Consequently, it is rejecting 850 megawatt to the ambient. Find the power to the air and how much air should be flowed to the cooling tower if the temperature cannot be increased more than 10 degrees Celsius. So this data we had obtained using the first law, because whatever is coming in, whatever is going out is equal to the deficit. So this is the heat transferred to the air. And we do not want that the temperature should increase by 10 degrees Celsius. So whatever is the heat output to the ambient, so the heat output to the ambient is balanced by the amount of air flowing through the cooling tower. So the amount of heat going into the cooling tower the cooling tower has a very peculiar shape. And there is some smoke coming out. So a power of 850 megawatt is being entered into the cooling tower, and a continuous draft of air with the flow rate m0 is taking the air away. So this amount of energy must be dissipated by the mass flux of air. Therefore m dot Cp delta T for air is equal to 850 megawatts. So m dot is equal to 850 into 10 raised to 6 divided by Cp into delta T. So the temperature rise max equal to 10 degrees Celsius. So this is multiplied by 10. Let us go to EES to find out the value of the specific heat. So the mass flux is equal to 850 times 1 is 6 divided by 10 times heat, where the specific heat is equal to. So let us quickly have a look into the help index. Thermophysical functions, spec heat. Okay, the spec heat returns the constant pressure specific heat of the specified substance. Air at T equal to the ambient is not given what the ambient is. Let us assume at 30 degrees Celsius. In fact, to avoid any confusion, we could have assumed that the pressure is known. So either temperature or pressure is sufficient. Okay, so temperature must be the only argument for an ideal gas. For air, temperature is the only argument. So that gives us a quick check of reality. So the specific heat is reported in kilojoule per kg Kelvin. So we must fix, because we have accounted for the megawatt over here, specific has to be multiplied by 1E3. The logic behind the multiplication of the factor 1000 is the fact that the default unit is in kilojoule per kg Kelvin, and we have already accounted for the megawatt over here. Okay, so this will give us a mass flux of this. This is the amount of mass flow per second that is required to balance out the massive heat flux being released into the atmosphere. This is a massive amount of heat being released into the atmosphere, so to balance that we must have a mass flux of 84,589 kg per second. So because it cannot be achieved often in one cooling tower, that is why we can have multiple cooling towers. Okay, so that's the key. So it's a very simple problem, but we must always keep in mind these units. These units are what create problems. 850 megawatt led to this. Specific heat output from the function is in kilojoule, that is why we have to multiply by 10⁻³ to make it into a normal unit of joule. Okay,